All right. So thanks for coming back. In this video, I'm going to start talking about capacitance, and um, and then we're also going to find potential differences with a different method. Specifically, we're going to look at configurations where we can use Gauss's law to first find the electric field and then work backwards to get the change of potential and then the capacitance. The starting point for this discussion is our rectangle of, which is kind of our roadmap, but it's our rectangle of pain and suffering. You can think of it however you want, you still have to do it. So let's kind of remind ourselves how that goes. I've drawn it several times in class. It's just sort of useful to remind ourselves how all the different quantities are related. Over here, we usually start with the force, and this is the force as observed by some hypothetical observer. Maybe a point charge, a test charge observer. And then over here, we had an electric field. And down here, we have potential energy of that observing point charge. Over here, we have the electric field comes from the sources. And down here, we have the electric potential coming from the sources. Let's fill in all the different relationships. So the relationship between the force on a test charge observer and the electric field coming from the source charges is the following. The force on the observer is the charge of the observer times the electric field of the sources. Over here, we have the usual relationship between force and potential energy, namely that the force equals minus the gradient on the potential energy. Or if you turn it around and use integrals, we find that the change in potential energy between 2 points equals minus the integral of the force dot dr, where we are integrating the force along the path connecting the 2 points. So between, say, A and B. So this is a line integral we would have to do. I think I used this kind of R, so I'll try to be consistent with that. Okay. Down here, the relationship between potential energy of the observer and the electric potential of the source is U of the observer is the charge of the observer times the electric potential coming from the source. And over here, these relationships mirror what we had for force and potential energy. We have the electric field of the source now. It's going to equal minus the gradient of the electric potential, or the change in electric potential equals minus the integral from A to B of the electric field dotted with dr. Okay, so that's kind of our rectangle of pain and suffering, if you want. So that's the rectangle that kind of maps out how all the quantities are related. So it's useful to write it out just so we kind of know what to do. All right, I'm going to erase that. Very good. Okay, so that's fine. And then the other thing that I mentioned in class last time we met, but I'll remind you now, is the definition of capacitance. So capacitance, C, is defined, the way I remember it is always to say that Q equals C times V. Now really, that's not quite right. It really should be delta V, but you know, life's short, and if you have to write everything all the time, you just get tired. So most people just write Q equals C times V, and it's implied that you're always looking at potential differences across the capacitor. Or if you turn it around, it says C equals Q divided by V. Now, capacitance is going to, when we have devices, the capacitance measures how much charge you can get per volt. So the unit of capacitance is going to be charge per volt, and we call that unit a farad, named after Michael Faraday. He's the one who came up with field lines and flux as a mental picture. So clever guy, especially because he didn't have the formal education that many of the other kind of famous people involved with all this do. All right. Let's also kind of spell out some things. Remember, okay. So we're going to start with a simple situation. We will start with a capacitor. All right. And we'll just start with a parallel plate capacitor, and we'll assume it's empty to start with. So we're going to imagine we've got a capacitor with charge Q and charge minus Q on this side, and this each side. And we will say that they have an area A. We'll say that the areas are the same. Now, for many practical purposes, we can pretend that the areas are almost infinite, and that allows us to make various simplifications. So if that's the case, rather than studying Q and A, we want to write these properties down in terms of sigma. Okay, so let's do that. So we're going to say we're going to have surface density sigma here and minus sigma here. And the goal is to find, if we say these are separated with a distance d, the goal is to find delta V. All right, so we want delta V. Oh, and I should have said this. When we find capacitance, it should be a positive quantity. So we want delta V to be a positive number so that we can read off the capacitance. If not, you just reverse it. Okay. Well, how can we find delta V and then eventually find capacitance? And we want it to be a positive quantity. And to do that, we remember that when you are near a positive charge, the potential is large and positive. And when you're near a negative charge, the potential is large and negative. And we want to go to find delta V between these, and we want the positive thing. So we want to start on the low side and finish on the high side. So we actually want to find delta V. We want to take the result at plus Q minus minus negative Q. Right? So we want to start here and finish here. Okay. To find delta V, we're going to use the integral formula. So we're going to say that is equals minus the integral of the electric field from the lower potential to the upper potential. So that's going to be, let's see. Let's say that this is at, just so we can choose coordinates here. Let's say this is x equals 0. And we'll say then that this is x equals d. So we're going to integrate from from d to 0 of the electric field dot dr. Now, when you're walking side to side in the along the x-axis, dr vector is just going to be dx x hat. And the electric field in the center, we already found that the electric field for a parallel plate capacitor is simply sigma over, for one plate it would be 2 epsilon naught, and because the two electric fields add up, you get sigma over epsilon naught. And it would point from the positive to the negative. So that would be times x hat. So when I plug everything in here, I get minus the integral from d to 0 of sigma over epsilon naught x hat dotted with dx x hat. And the dot product just is trivial, goes away, gives me a factor of 1. Everything else is constant, and I am integrating from d to 0, so I can reverse that integral, get rid of that minus sign, and I'm left with sigma over epsilon naught times the integral dx from 0 to d, but that's nothing other than sigma over epsilon naught times d. Very good. So that is the formula for delta V. And we arrived at it using the fact that we knew the electric field, which came from Gauss's law. To find the capacitance, we want to express everything in terms of Q, which means we have to rewrite sigma in terms of Q. So that's simple enough. I take this answer and I rewrite that to find V equals sigma is Q over A. So sigma is, so V equals Q D over A epsilon naught. Using the definition of capacitance, it's the definition of capacitance, then I find that Q divided by V is A epsilon naught over D. And that is the capacitance for a parallel plate capacitor filled with vacuum. Okay. Some comments. Capacitance, when you work it out, is always geometry times epsilon naught. Or when we get to dielectric materials here in just a bit, you might replace epsilon naught with the appropriate parameter for a different material. But it's always geometry times that. And it has units. Dimensionally, it's a length times epsilon naught. But the geometry part typically won't just be a length. It can involve logarithms and other things as well. So it can be more complicated. But unit-wise, as units of length times epsilon naught. And it's always something geometric times epsilon naught. It never, ever explicitly depends upon Q or V. So there will never be Q or V in the formula for capacitance. It's always geometry times epsilon naught.